All right, what is a red-black tree? Well, a red-black tree is just a binary search tree that uses red and black nodes. These red and black nodes help us to determine how we rebalance after an update operation, which, by the way, is a big O of 1 time complexity. A red-black tree has all the same properties of a binary search tree plus 4 more. Okay. The first property is called the root property. And this just says that the root is always black. All right, this is pretty simple. The root of any red black tree must always be black. The second one, the external property, says every external node must be black. Here you can see that not all of the external nodes are black. Some of them are red. Actually, here, 4 of them are. However, I just want to show you this because in the next example, and from there on forward, and a lot of examples you might see online, we show all of these external nodes and their null leaves. So all of these external nodes have 2 children that are null, but in a red-black tree, all null nodes are considered black. When we show them, they actually become the external children, so we can always satisfy this property. The third property is the red property. This says children of a red node are black. Basically, this is saying 2 red nodes cannot be connected to each other in a red-black tree. And if they are, then we have a problem and we need to fix it. We'll see this a lot in the insertion. The last property is the black death property. This says all external nodes must have the same number of black ancestors. So if you take all the external nodes and their path up to the root, all of them must have the same number of black nodes up to the root. And if they don't, then we have a problem and we need to fix that as well. We'll see this a lot in deletion. All right, so let's look at another example of a red-black tree. Okay, here's another example. And as I mentioned, the second property, the external property, says that all external nodes must be black. Okay, well here clearly 3 of them are red. All right, so this doesn't satisfy it. However, what we do in a red-black tree is we show all of the null nodes of these external nodes, and then they become the external nodes. And in a red-black tree, all null nodes are considered black. And from here on forward, we're going to show these nodes, and we can always satisfy this property. So this is a real representation of a red-black tree. We're going to go over insertion, and then we'll go over deletion. All right, we'll go over the properties of each, and then I'll go through all the cases. So there's a lot to uncover here and a lot to learn. But I believe in you, and you can do this, and I'm going to help you do this. So let's get started with insertion. The first thing we need to understand is when we do a red-black tree insertion, we're really just doing a binary search tree insertion first. That's the first thing we do. And then all the operations after that will be performed by the red-black tree on the node that gets inserted. Okay. So the first thing you do is a BST insertion, and then we'll worry about that node we just inserted. Okay. A few properties of insertion. Well, we might have to do some rotations, and these are just the same rotation we do for an AVL and splay tree. Okay, there's 4 cases, 2 single and 2 double rotations. We may have to do some recoloring, so we just change the color of the nodes. And kind of to determine what we do, we first check the parent node and then the sibling node. So the parent node would be the parent node of what we just inserted, and then the parent node sibling node. Okay, this will make more sense when we look at another example and we actually do some labeling. But this is how we determine if we need to rebalance and how we rebalance. Okay, if we insert a node and its parent is black, then we're done. You don't need to do anything else to the tree. All right, it's balanced. If we insert a node and its parent is red, we have what's called a double red problem, and we need to fix it. Okay, so what's the double red problem? Well, the first thing is when you insert a node, it is always red unless it's the root. Then you change it to black. Okay, if the parent of an inserted node is red, we have this double red problem, and it violates the red property, the third property, which says children of a red node are black. So to fix this, there are 2 cases that we have to remember. The sibling, which we label S, of Y, and Y is the parent of the inserted node, is black, then we do something. If the sibling of the inserted node's parent is red, then we do something else. All right. So there's two cases. Basically, we care about the sibling of the inserted node's parent. Okay. All right. Let's look at the first case. All right. This is where the sibling is red. Well, what does that mean? Let's take a look at an example red black tree that I have here. And the first 5 steps here on the left are going to be the same for all the insertion cases, okay, that I'm going to show you. I just want to remind you what they are, and so you have something to look at for every case, okay? So we either do some recoloring, we may do some rotations, and I'll remind you that all nodes inserted begin as red. If it's the root, we just go ahead and change the color to black, all right? And the inserted node is always labeled X. We fix a double red problem, okay? That's again when we insert a node and its parent is also red. And if that's the case, then we want to check the sibling node of Y, and Y is the inserted node's parent. If the sibling is red, we just recolor. If the sibling is black or null, then we rotate and then recolor. Okay, and remember, anytime we insert, it's always like a binary search tree first. All right, so in this case, let's go ahead and do one. So for case number 1, let's insert node 18. So in a binary search tree, 18 is going to be the right child of 12, just like this. And we do have a double red problem. Okay, 18 and 12 are both red, so we have to fix this. Well, the first thing we want to do is label. The inserted node is labeled X, its parent Y, Y's sibling is labeled S, which is just the other child of Z, and Z is the grandparent of X. Now, so let's go back to step number 5. If the sibling is red, recolor. Well, in this case, it is. So we have to do some recoloring. At step number 6, Y and S become black, and then Z becomes red. All right, so let's go ahead and do that. We change the coloring. However, Z is the root in this case. And again, property number 1 of a red-black tree. The root is always black. So we have to change that to black. Okay. And in this case, we are done. However, if there's a larger tree, the double red problem may reappear at node Z, and we just have to redo the process. That's all we have to do. So for case number 1, this is it. Now, case number 2 is when S is black, not red. Okay. So again, we have the first same 5 steps to remind you what we do. We're going to take a look at an example red-black tree. And this time, let's insert 13. So in 13, just like a binary search tree, is going to be the left child of 15. Let's go ahead and label. Remember, X is always the node that we insert. Then we label Y, Z, and S. Okay, Y is the parent of X, Z is the grandparent of X, and S is the sibling of Y. Okay, again, all null nodes are black. So if the sibling is black or null, we rotate and then recolor. Okay, so this is the case where S is black, and this happens to be an LL rotation case, all right? Because if you look at Z, it has a left node and then another left node. So the tallest child of Z is this left child, and the tallest child of Y is its left child, okay? So we label them Z, Y, and X in a straight line. And an LL case, just like an AVL tree or split tree, it's a single right rotation. The first thing we do is perform a single right rotation around Y. All single rotations are around Y, and all double rotations will be around X. So let's go ahead and do that. And then we relabel. Okay, so we finish the rotation. The next step is to do some recoloring. So X and Z become red, and then Y becomes black. And we're done. Okay, why are we done? Well, we satisfy all the properties of a red-black tree. The root is black. All external nodes are black. The red property is satisfied. We don't have 2 red nodes connected directly to each other. And the black depth property. If you take every external node here and each of the paths go to the root, there will be 3 black nodes on each of the paths. And that's perfectly fine. That's what we want. So X and Z become red, Y becomes black. All right, an easier way to think of this is in this small subtree that we're doing these rotations around. When we're done with the rotation, the new root of this subtree will become black and its 2 children will become red. Okay, we'll see more of these cases might make a little more sense. The next case is when S is still black, but it's the RR case. Okay, let's take a look at another example. Now let's insert the node 20. So just like a binary search tree, it's going to be the right node of 18, or the right child of 18. So let's go ahead and label X, Y, Z, and the sibling. Well, the sibling is black, so we're going to do a single rotation around Y. In this case, this is a single left rotation. We relabel, and then we do some recoloring. X and Z become red, and then Y becomes black, just like the last case. Let's move on to the third subcase in case number 2. Let's take a look at this red-black tree. And this time, we're looking at the LR case. All right. Well, let's go ahead and insert 13. That is going to be the right child of 10, just like in a binary search tree insertion. All right. Now, this is another double red problem. We go ahead and label X, Y, Z, and S. All right, well, the sibling is black, so we have to do some rotations and recoloring. This time, it's going to be a double rotation around X, like I mentioned before. The first thing we do is a single left rotation, and then we do a single right rotation, and relabel, of course. Y and Z this time become red, and X becomes black. Like I mentioned, an easier way to think about this is because these nodes are recolored a little differently than the single rotation cases. How I would think of it is the new root of this little subtree here. So this time it's X. That's always going to be black. And then its two children will always be red. That's an easier way to think about it. And for the last subcase for the insertion case number 2, we have this red-black tree, and this is the RL case. Let's go and insert 17, which in a standard binary search tree insertion will be the left child of 18. Now again, we have a double red problem. We want to go ahead and label X, Y, Z, and S. The S is a black node, also because it's null, so we have to do a rotation and recoloring. This is a double rotation around X. We'll perform a single right rotation, and then a single left rotation. Now X is the root of this subtree. Now we do some recoloring. Y and Z become red, and X becomes black. And we're done. In all these cases, after we're done, all 4 properties of a red-black tree are satisfied. The root is black, all external nodes are black, the red property is satisfied, no 2 red nodes are directly connected to each other, and the black depth at every external node is the same. All right, let's get started with deletion properties. What do we do in a red-black tree deletion? Well, the first thing is you perform a binary search tree deletion. Okay, so any operation after that will be performed on the node that gets deleted or promoted. Okay, and in a red-black tree case, it's pretty much always the node that gets promoted. Okay, and we'll make more sense of that in a minute. So we could have to do some rotations. So it's the 2 single rotations and the 2 double rotations. We may have to do some recoloring, which just simply changing color of the nodes. And what we have to look out for is if we delete or promote a red node, then we just make it black and we're done. Okay, that's a simple one. Kind of like the insertion properties, we had a simple one where if the inserted node is red and its parent is black, then we're done. Okay, so the last property to look out for is if the removed node was black, we have to restore black depth property. Okay, so we create a double black problem. What is this double black problem? All right, let's go a little bit more in depth about it. Well, again, when we remove a node that is black, this will make the black depth property imbalanced. That's property number 3 of a red-black tree. Okay, so at some external node to its root, well, the path has 1 less black node now. All right, so when we delete the black node, it can become null, which is black, or the node that we're replacing it with or promoting is also black. So like the in-order successor is also a black node. Well, to temporarily restore this black depth property, we make that node a double black. We give it another ring around it, denoting it stands for 2 black nodes now. Okay, and with some examples in all these cases, this will make more sense. So After we do that, after we see that we have a double black problem, we have one of three cases that we can solve for it. The sibling y of p is black and y has a red child. Sibling y of p is black and both children of y are black. Or sibling y of p is red. Okay. There's some labeling involved here. Just want to get this information out there. There's a lot going on with deletion. Okay. So just follow along and we'll get through this. You can do it. Let's get started with the first case. All right. The first case is also a terminating case, which I'll get to also in a couple of minutes. So let's take a look at an example red-black tree. All right, here's an example tree, and let's say we want to remove 24. Well, just like a standard binary search tree deletion, we make sure we find 24 first, and we do find it, okay? So in just a standard binary search tree, we would just delete this, and then that'd be it, okay? But in a red-black tree, this causes the black depth property to become imbalanced. From all the external nodes here to the root, they all have 3 black nodes. If we remove 24, these 2 external nodes on the right, well, there'll only be 2 black nodes up to the root. Okay, so there's already an issue right there. So what do? Well, we promote one of the null nodes and make it a double black node. Okay, so now that null node with the ring around it counts as 2 black nodes to temporarily restore the black depth property in this tree. Okay, it's just temporary though. So once we do this, now we have to get rid of that somehow to make the tree balanced. All right, so the first thing we do, and I like to do, is like to label. All right, so the deleted node or the promoted node, we label P. The sibling of P will be Y, and it has a red child X, and the grandparent of X will be Z, or the parent of Y is Z. Okay, so we've done some labeling now. So this is where case 1, sibling Y of P of the promoted node is black, and Y has a red child. All right, that's case number 1. So next thing we do is we have to restructure. We say restructure X, and if it's a single rotation, we'll end up just rotating around Y. Okay. In this case, this is an LL case. So just like insertion, we start at Z. Well, its tallest child is the left child, and then Y's tallest child is its left child. So this is a left-left case. Well, we do a single right rotation around Y, just like this, and we relabel. Okay, now that we've done that, now we just recolor. So we change node X and Z to the color black, and node Y, now the parent of X and Z, becomes the former color of Z. So we just do this. So now Y is red. Okay, and what we've done is we fixed the problem. And we can get rid of this ring now around the promoted node because we fixed the black depth property. Okay, the whole reason of having a double black node is because when you delete a black node, you create a black depth imbalance. Okay, so property number 3 becomes imbalanced. All right, so we have to fix that. So we temporarily create or make the promoted node a double black node so it counts as 2 black nodes. Okay, because remember, we get rid of one, so now we have to add one to a single node, making it a double black node. All right, and now we've done the rotations, we've done some recoloring, and we can get rid of the double black node, just make it a single black like it was. And we restored balance. So if you take any external node here, they will all have a path to the root of 3 black nodes. Okay, and we're done. Case 1 is a terminating case. So all of the cases, all the subcases for case 1 are terminating cases, all right? Because for case 2 and 3, we may have to come back to case 1, right? Because you could have to propagate the problem up the tree, then eventually you get to case 1 or the root. All right, let's go to the next subcase of case 1. All right, this is very similar. This is a right case. So let's say we want to delete 15. Okay, so we promote a node up, and now we have to make this node a double black node so that the path from this now double black node to the root is also 3, just like every other external node's path to the root. We do a restructuring, but first we label X, Y, Z, and P, where P is the promoted node, and we do a restructure around X, so we basically do a single left rotation around Y. Let's go ahead and do that. we change node X and Z to the color black, and then node Y, now the parent of X and Z, the former color of Z. Okay, so Z was red, so now Y becomes red. And we can get rid of the double black node that was P. Okay, so P was a promoted node. We had to temporarily make that a double black node. And we're done, because now the black depth property is balanced again. Let's move on to the next subcase. Let's take a look at this tree, and we can say, let's delete 24. Okay, well, we deleted 24. We promoted one of the null nodes up, and now we have to make the double black node so that the black depth property here is satisfied. And we have 3 black nodes from that external node up to the root. Okay, just like every other external node here has 3 black nodes going to the root. All right, let's go ahead and label. So we label X, Y, and Z in the promoted node P. We want to restructure around X. Well, this case is the LR case. If you take Z, its tallest child is its left child, and then Y's tallest child is its right child. Okay, so this is the left-right case. Well, let's do the restructuring. This is double rotation, so we do a single rotation to the left, and then a single rotation to the right. All right, and we have our labeling again. And now we just recolor. Okay, so we change node Y and Z to the color black, and node X, the former color of Z, which was red. Okay, and then we can get rid of the promoted node's extra black node. Okay, it's not a double black node anymore, and we're done. Okay, let's go over one more subcase, which is it's the last one. And here is another example of a red-black tree, and I want to delete 15. Well, we delete it, we promote one of the null nodes, and now that is a double black node. We have to solve for that. Let's label first. That is the promoted node P. Its sibling is Y. Okay, then X is the child of Y, and Z is the parent of Y. Okay, we restructure around X. This is the RL case. This is a right-left case. This is double rotation. We're going to do a single right rotation, and then a single left rotation. Then we do some recoloring. We change node Y and Z to the color black, and then node X, the former color of Z, which is red. We change the color just like this, and we can get rid of the promoted node's double black problem. Now it's just a single black node like it was before, and we're done. Okay, I hope you've been following along. This is a lot, okay? This is a lot. But you can do this, and now we can move on to the second case, which doesn't have all of these subcases like this does. So case number 2. This is when the sibling Y of P is black and both children of Y are black. In case 1, one of the children of Y were red. Okay. Now let's delete 12. Okay. Again, this is just a normal binary search tree deletion. We promote the null node, and we have to make it a double black so we can temporarily solve the black depth property issue. Well, the node that we deleted or promoted is P. We label the sibling Y and their parent Z. Okay. We're not worried about anything being X in case number 2. All right. What we do is we do some recoloring. All right. We change the color of P from double black to black, and the color of Y from black to red. Okay. We do this. Now, this is where the case deviates. All right. If Z is currently red, color it black, and we're done. If Z is black, we color it double black, and then we would propagate the issue up and call a method that takes care of these cases on Z. All right. But let me go back. Z is red, so we just color it black, and we're done. Okay. Because now every external node here, all 5 null nodes, if you go up to the root, all our paths have 3 black nodes. We're done. Okay. This is when Z is red. The other subcase for case number 2 is when Z is black. Let's go ahead and delete 20. This is a black node, and we're also replacing it with, or promoting it with another black node, which is the null node. Let's go ahead and do that. Now we have to make this a double black node so that we have 3 black nodes from this external node to the root. Okay, because if you go the three's children, which are all null nodes, but they're black, they all have 3 nodes going to the root. All right, we have to make this balanced on each side. All right, well, let's label the sibling Y, the promoted node P, and their parent Z. Go through the same case. We change the color of P from double black to black, and the color of Y from black to red. All right, this is where it deviates again. If Z was red, we would just color it black and we're done. But it's not this time. If Z is black, we color it double black. And we would propagate this issue up and call a method that takes care of these cases on Z. If it's the root, we just make it black. In this case, it's just black, so we would be done here. We just get rid of the double black we have here. This now satisfies the double black property. Moving on to case number 3. This is when the sibling Y of P is red. Let's take a look at an example. Let's first delete a node. How about 25? We delete it and we promote one of the null nodes up. Now let's do some labeling. So that is labeled P, its sibling is Y, and their parent is Z. What we do here is we perform a single rotation about Y and Z. Let's go ahead and do that. We recolor Y black and Z red. To fix the double black problem at P, we now execute case 1 or 2 onto P. All right, now remember, case 1 is a terminal case, meaning it'll fix it. Case 2 could be terminal, or it may not be, okay? It's only going to be terminal if the parent of P is red, all right? Which is one of the cases we just did. So just to kind of re-clarify here, if the sibling Y of P is red, okay, after we delete it, we just label them Y, P, and Z, all right? We just do a single rotation about Y and Z. That's it. We recolor Y and we recolor Z. All right, now we have a double black problem at P, which was the promoted node. Then we execute case 1 or 2 on this, and we keep doing that until we're done, okay? So we execute case 1 or 2 on the promoted node here, which is P. Case 1 is a terminal case, and one of the 2 subcases for case 2 is also terminal. All right, so eventually you get to where you don't need to do anything anymore. All right, and you fix the double black problem. All right, but that's it for all of the deletion cases. Thank you for sticking with me. And next, we will go over some examples. Okay, let's go through an example now. Let's do some insertion, and then we'll do some deletion. Okay, we're going to start with a blank slate, a brand new red-black tree. So let's go and insert a node, and we're going to make it 8. So when you insert a node, it's always starting out as red. Okay, it's always a red node when you first insert. However, because the first node in a tree is the root, we have to make it black because that's what the first property of a red-black tree says. The root must always be black. So we just make this black. Okay, and we're done with that one. Well, the next node we insert is 12. And again, all insertion and deletion starts out with the binary search tree operation. So 12 is going to be the right child of 8, just like this. And again, we always insert a node as red. Well, this is kind of easy. This is kind of an easy one because when you insert a node, you first check the parent. Well, the parent is black. And if the parent is black, remember, we're done. We don't need to do anything else. Everything here satisfies all of the red-black tree properties. All right, well, let's kind of mix things up a little bit, and we're going to insert another node, and this time it's going to be 20. Well, 20 is going to end up being the right child of 12, and we have an issue here. This is the double red violation or double red problem that we have when we insert, okay? How do we figure out what to do? Remember, the node we inserted is X, its parent is Y, so 20 is X, 12 would be labeled Y. We want the sibling of Y. We check to see what color that is. So the sibling of Y is a null node, and null nodes are black. Well, this means this is case number 2, all right, when the sibling is black. And this is an RR case. This just means we have a simple single left rotation. So let's go ahead and do that. And then after we do the rotation, we just have to do some recoloring. So 8 and 20 will be red, and 12 will be black. And we're done. Now, let's insert another node. Let's insert 15. Well, 15 is going to be the left child of 20. And again, we have another double red violation. We need to see what the sibling node is. 15 is labeled X, its parent is labeled Y, so 20 is Y. Its sibling is 8, and 8 is a red node. Well, this refers to case number 1. So there's no rotations here, we just do some recoloring. So we're going to take the sibling node and Y, and we're going to make them black. Then we take the grandparent and make it red. However, because the grandparent is also the root of the tree, remember, red-black tree, property number 1, the root is always black. So we have to change it to black. And now we're done. Okay, let's insert another node. Let's insert 3. Well, 3 is going to be the left child of 8. And the first thing we do is check 3's parent node. Well, it's not red, so we don't have to worry about the double red violation. It's actually black. And when it's black, we're done. That's it. This is an easy one for insertion. Okay. Now let's insert another one. Let's insert 5. Well, it's going to be the right child of 3. And here, you can see that we do have a double red violation. Remember, when you insert, you always do it just like a binary search tree first. All right. And then every operation after that for a red-black tree is on that node that we inserted, okay? So look at 5. Again, its parent is red, so we have this double red violation. Well, what case is this? Well, we have to look at the sibling node. 5 is X, and then its parent, 3, is labeled Y. Well, what's Y's sibling? Well, it's a null node, and all null nodes are black. So the color of the sibling is black. This is case number 2 for insertion. And this happens to be an LR case. All right, because if you take a look at node 8, which would be labeled Z, it has its tallest child is 3, which is the left child, and then 3's tallest child is 5, which is its right child. So this is a left-right node case. A double rotation will be needed. Let's go ahead and do that. We do a single left rotation and then a single right rotation. All right, but we're not done. We have to do some recoloring. Well, we make the root of this subtree, which is 5, we make it black, and both of its children, Y and Z, which we wouldn't be labeled, red. All right. All properties of the red-black tree are satisfied. Now let's go over some deletion. Okay, let's delete some nodes. Well, let's start off by deleting 5. All right, so we delete 5. We need to find the in-order successor because we're first doing a binary search tree deletion. Well, the in-order successor to 5 is 8. So we're going to replace 5 with 8. Okay, now as I said, when we delete, if the node to be replaced or the promoted node are red, all you do is change that node to be black. So we change 8 to be black, and we're done. That's it. So let's go ahead and move on to the next one. Let's say we want to remove 15. Okay, well, let's do that. Again, if the node to be removed or replaced is red, or the promoted is red, then all we have to do is change it black. Well, this is a null node that got promoted. We don't have to change it black because it already is. And we're actually just done. That's it. Okay. This one's also really simple. Now, let's do one that's not so simple. Let's delete 20. Well, we are deleting a black node, and the node to be promoted is null, which is also black. This gives us a double black problem. Okay, so this is the node, this null node is now a double black. All the other nodes, all the other external nodes have 3 as their black depth up to the root. This one only has 2, but we make it a double black, so now it has 3 temporarily. Now we have to figure out what case is going to solve this problem. Well, the sibling of the promoted node, so the sibling of this null node, is black and it has a red child. Well, this is case number 1. We just label them here, okay? Here are the steps again for deletion. We labeled all the nodes, and we're going to restructure around X, the red child, okay? This is really just going to be a single rotation to the right. So this is a left case. And really, we're just going to be restructuring around Y, not X. But the method that we coded would take care of that. All right, so this would be a single rotation. we do the relabeling. And the third step is we recolor. We change node X and Z to the color black, and node Y the former color of Z. Well, the former color of Z is black, so Y just stays black. And we're done, okay? Remember, in deletion, case 1 is always terminating. So once you do this once, you're done with the whole tree. It's all balanced. I hope this has helped, seeing some real examples. I suggest doing more because it's only going to help you. There's a good bit going on with red-black trees. Just do some more examples, and you'll definitely get there, okay? I believe in you. The first thing we need, though, is the node class. Let's begin. I already have the node class set up, so we'll say private node parent, private node left child, private node right child. Have the we need the height property next, so private int height property. I'm going to set it equal to 0 to begin with, and then private int value, the actual value of the node. Okay, and next thing, it differs on the IDEs, as I mentioned in some of my other lessons. I'm just going to create my getters and setters. I'm going to right-click in IntelliJ, go to Generate, Getter and Setter, highlight everything, and then hit OK. All right, now we have the node class set up. All right, this is pretty standard. We've kind of done this before. So now let's move on to the Balanceable Tree class. Okay, let's get started. First thing we need is a root field. So private node root. Let's create our constructor, public Balanceable Tree. Give it the value as the parameter. Then root is going to equal this new node. Okay, whatever the value was put in for the constructor, the root is going to equal that. So we have our first node of the tree. Then we need a method to retrieve the root. So get root, we're just going to return the root. All right, so we're going to set up our binary search tree class. We have already created this in another lesson. However, this is going to be a little different. And the reason is because we have auxiliary methods kind of inside of the searching, inserting, and deleting, because those methods are going to be what we do after we do the regular binary search tree operation. So like I mentioned with an AVL tree, you do a regular binary search and then you do the rotations afterwards. All right, so we're going to have those methods inside of these binary search tree methods to tell us what to do after we do the regular binary search tree operation. Okay, it'll make more sense once we start coding it. So let's get to it. So public, we'll begin with searching. So public node search, give it the key as a parameter. Node found. It's going to be equal to search. We're going to have a helper class. Give it the root and the key. All right, and then we're going to have what's called a rebalance access node found. Okay, and we just want to return node found. All right, so we need to create the search helper method first. Private node search helper. We're going to give it a node parameter and an int parameter for the key. Okay, because we're going to be using some recursion, and we need to always give it the node and the key. Okay, so if key is equal to the node.getValue, so we found it, the key has been found, we're just going to return the node. Else if key is less than node.getValue, so this is going to be the left child. If node.getLeftChild is equal to null, return node. And just return search helper node.getLeftChild. And then we have to give it the key as well. Okay, so if node.getLeftChild equals null, then we're just going to return the node, because when we search for something, if we don't find it and we're at the leaf, then we need to return that leaf node, because that leaf has no other children and we haven't found it. Okay. Otherwise, if we don't hit a null node, then we just keep using recursion until we do find it. All right. Else, if node.getRightChild is equal to null, then return node. So if what we're searching for is greater than the current node, we go to the right child. Otherwise, just return search helper, do some recursion, node.getRightChild, and give it the key as well. Okay, so this is the searching, and the rebalance access, we will give this method later, but it's still going to be an empty method within the Balanceable Tree class. We will fill out that code for the AVL tree, splay tree, and red black tree classes themselves, not in the Balanceable Tree class, okay? It'll be saved for those classes. All right, well, we did the searching. Now we can move on to the inserting. So give ourselves some space here. So public int insert, and we give it the key. Then we create a new node based off of this key, okay, because this is what we want to insert. And then we need to search for this key to see if it exists first, okay? If it doesn't exist, then we can go and insert it. Found node equals search helper, the root, start at the root, and search for the key. If found node equals null, found node equals found node dot get parent. If found node dot get value is equal to the key, meaning we found it, we're going to say rebalance access of this found node. So this is one of the other methods that are going to help rebalance the tree after you search for something. Okay, we'll get to that in a little bit. Else, if it doesn't equal the key, then if key is less than found node dot get value, meaning it's going to be the left child, then we say found node dot set left child, the new node. Okay. Else, found node dot set right child to the new node. Then new node dot set parent to the found node. And then after we've done the binary search tree stuff, we will need to do the rebalance insert method. So rebalance insert of this new node. Okay, so what do we do here? If found node dot get value equals the key, that means we found it. Then in some instances, we'll have to do something such as a splay tree, which you'll learn about. We have to splay after we do it. So we have a method called rebalance access, which will fill in a splay tree class, okay? Otherwise, if it doesn't equal the key, and this is the parents, this might be the leaf, okay? If the key is less than found node.getValue, then we set its left child to the new node, all right? Otherwise, we set its right child to the new node. And then finally, new node.setParent of the found node. So we're just kind of setting the parent-child relationships here. After we do the binary tree insert, then we have to do the rebalance insert method, okay? So after we do a regular binary search tree insert, then we have to do something on that new node that we just inserted. And that'll be left up for the AVL tree, splay tree, and red-black tree classes, okay? And then finally, we're just gonna return the key that we started with. All right, now we have the deletion. So let's go ahead and start with that. Public int remove, give it the key. We'll say node found node equals search helper, give it the root and the key. So we need to still find the key when we do a deletion to see if it exists in the tree. If we find the node, so found node.getValue equals the key, then we return remove helper, found node, and the key. So this is the recursive part when we find it, all right? Then we return key. So if we find it, we're going to create this return helper method to deal with it. Because remember, with deletion, there's a few cases. There's actually 3 cases for a binary search tree deletion, and we have to take care of those. So public int remove helper, give it a node and a key, or int key as a parameter. Node successor equals node. Okay, so we're just kind of setting the successor, the in-order successor variable, just to the current node. Then if has no children, this node, so this node has no children, we're going to create this method. Then it's the leaf node, so we can say remove leaf node, and the node, give it the node that we want to remove, and the node dot get value. Okay, and it might make a little more sense once we code this in a few minutes. Then the next case is if it has one child, if the node we want to delete has one child. If has one child, then replace node with child node. Okay, so we're going to replace, if it has one child, then we just need to, we delete the node and then we move its child up. Okay, if has two children, so if the node has two children, as the last case, we need to say the successor equals get in order successor. Node starting with the node.get right child. So we're going to go to its right child and then try to get the in order successor. Okay. So we say node, the current node dot set value to the successor dot get value, whatever we found. And then again, we're going to call remove helper successor on the successor node, and then give it the successor dot get value because that's the one we're trying to find. So after you find the in order successor, remember you do the replacement, then recursively go and call remove helper. You're only going to get either the no children case or the one child case. Okay. And then finally, after all that, okay, because these are balanced trees that we're going to be dealing with, we're going to call the rebalance delete method. And then return node.getValue. Okay, that was kind of a lot. All right, so let's recap really quick. So in a binary search tree deletion, we first check what case it is. If it has no children, then we just remove the leaf node. If it has one child, then we replace that node with the child node. If it has two children, we find in order successor, and then set the node we wanted to remove, set its value to that in order successor, and then we're going to call the same method, the recursion. We're going to use recursion to say remove helper on the successor node and its value. So we want to find whatever value that was, and then we need to remove that from the tree. You do a replacement with the in order successor, and then after you do that, you still have to remove the original node that was the in order successor. Okay, and then after we do all the binary search tree stuff, then we call rebalance delete on that successor's parent, and which will fill that out in the AVL tree, split tree, and red black tree classes. And then we just return the node that we were looking for, its value. Okay, well, we got some methods to fill in, so let's go ahead and get started. We'll go ahead and do the if statement methods. So private boolean has no children. Just give it the node we're going to check. If node.getLeftChild equals null, and node.getRightChild equals null, return true. Otherwise, return false. Private boolean has one child, give it the node. If node.getLeftChild does not equal null, and node.getRightChild does equal null, or if it's just the other way around, node.getLeftChild equals null, and node.getRightChild does not equal null. Okay, if that's the case, return true. Otherwise, return false. Okay, then for the last one, private boolean has two children. Give it the node as the parameter. This was a little easier. Node.getLeftChild does not equal null, and node.getRightChild does not equal null. Return true. So it has if both children are something other than null. Otherwise, return false. Okay, now we have to code when we have to remove the leaf node. All right, so private void remove leaf node. All right, you want to give it the node and a value. So node parent node, just declaring this. If node.get parent does not equal null, parent node equals node.get parent. Otherwise, so if we're checking to make sure that we're not the root, basically, else parent node equals node. If parent node dot get left child does not equal null, and parent node dot get left child dot get value equals the value we're trying to remove, then we say parent node dot set left child to null. Otherwise, parent node dot set right child to null. So what we're saying here is if the left child is not null, if that's the one we're trying to remove, okay? So we went up to whatever we're trying to remove here, whatever leaf node we're trying to remove, go to the parent node if possible. Then we say parent node dot left child does not equal null, and if that value equals the value we're looking for. So it's got to be either the left child or the right child. So if those things are true, then we just set its left child to null, getting rid of that leaf node. Otherwise, we get rid of the right child. So by setting it to null. All right, let's give some space here. And moving on to replace node with child node. So private void replace node with child node. Just give it the node as the parameter. And then node child. Now this can be, we're using a tertiary operator. So node dot get left child. So we're getting the left child of the node we're trying to replace. Okay, so node dot get left child. If it does not equal null, if that's true, then we return node.getLeftChild. And then with the colon, this means otherwise if that statement is false. If node.getLeftChild does not equal null is false, then we return node.getRightChild. Because remember, this case is only with one child, so we're just trying to determine if it's the left or the right child that's not null. So if child does not equal null, child.set parent node.getParent. Okay, so now we're kind of breaking the references. So we want the child node to equal the parent that we're trying to replace, its parent. If node equals root, root equals child. Else, so that's just kind of like a case that we have to look out for, is if the node is also equal to the root. So else node parent equals node.getParent. If node is equal to parent.getLeftChild, parent.setLeftChild, child. Otherwise, parent.setRightChild, child. Okay, so we're just doing the parent-child relationships, getting rid of the node we're trying to replace. So we said node parent equals node.getParent. Okay, so that's the grandparent of the child that the child node we just coded for. Then if node is equal to parent.getLeftChild, then we want to break it by saying parent.setLeftChild, the child node we just kind of coded for as well. Okay, so we're just breaking up the relationship between the child node, the parent, and the grandparent. Okay, and we're done with that. The last one is to get the in-order successor. So private node get in-order successor, give it the node, okay. So when we do this, we went to that node's right child first. Okay, so while node.getLeftChild does not equal null, node equals node.getLeftChild. We just return the node. Okay. There's a chance that we could start out and that right child is equal to null. This will take care of that. But to get the in-order successor, we go to the right child and then find the furthest left child in that subtree. And we're done with the binary search tree stuff. Now, the whole thing with balancing a tree is we have rotations, and we have to restructure things after these rotations. Okay. All the subtrees, we have to relink them to other nodes after the rotations. So next, we're going to take care of that, okay? And it's a little bit more involved, so stay with me. So the first thing is the rotate method. All right, we just learned about rotations when we talked about AVL tree, and we're pretty much going to be doing that for all of these balancing trees, okay? So rotate. So public void rotate, give it a node that we're going to be starting with. So node x equals this node. We're going to do some labeling here within the code. Node y equals x dot get parent. Okay, this is familiar. We just went over this in the AVL tree explanation. Node z equals y dot get parent. So if z is equal to null, this means that y was at the root of the tree since z is the grandparent of x. Okay, so if z equals null, that means y is currently the root, all right? Then we say root equals x dot set parent null. Else, we're going to have a relink method. This will make sense here in a little bit. We're going to say relink z and x, and its left child will be if y is equal to z dot get left child. Okay, just stay with me for now. Okay, if x equals y dot get left child, so x is a child of z, okay, because z does exist. All right, it's not empty, it's not null. So if x equals y dot get left child, so this is kind of the left case. Then we relink y and x dot get right child, and we're gonna say true, okay, because we want to make this the left child. X's right child will become y's left. Then relink x, y, and false. Now this means that y will become x's right child, okay? This will make sense here and in a little bit when we get to coding the relink method. Otherwise, if x does not equal y dot get left child, that means it's y's right child. This would be the LR or the RL case, all right? Then we get a relink y and x dot get left child, false. We don't want to make it the left child. This is x's left child becomes y's right child. Okay, so then we need to relink x, y, and we're going to say true. This is when y becomes the left child of x. Okay, and we're done with the rotate method. Okay, so we need to move on. We're going to have two more methods for all this balancing. Okay, so we're going to have a kind of like a main one called restructure. So public node restructure node x. So node x, this is denoted x because when we give a node in this restructure, okay, because it could be a single rotation or a double rotation, this restructure method is going to determine whether it's a single or a double rotation, all right? So node y equals x dot get parent, just kind of doing some labeling within the code as well, all right? Node z equals y dot get parent, which is kind of the grandparent now. So if x equals y dot get right child equals y is also equal to z dot get right child. So this is when everything aligns on one side. Okay, so this is like the LL case or the RR case. So it's just the single rotations. We're just going to rotate around y, okay, and then return y. Else, we do a double rotation around x. Okay, we need to rotate x to become the middle child, and then y will be either its left or right child. And then we need to rotate again because it's a double rotation. And then we return x. And finally, we have this relink method. So private void relink. We have the parent node, then we have a child node, and then we're going to determine whether we want to make it a left or right child. Oh, make left child. So if the child node does not equal null, child.setParent, parent. So we're going to set the parent to child link. Okay, and then next we need to set the child to parent link. If this third parameter in the method is true, okay, if it's true, then parent dot set left child to the child, okay? Else parent dot set right child. Okay, we are almost done. Just have a couple more small methods to create. One is a method that's going to help us later on in a couple other classes, and then we have to just code the skeleton methods for rebalance access, insert, and delete. Okay, let's wrap this up here. Public boolean is internal node as the parameter. This is just a helper method to determine if a node has at least one child, which will be used, I think, in the red-black tree later on. Okay. Return has one child node or has two children node. Okay. Okay. Now we have to create the rebalance methods. Public void rebalance access node public void rebalance insert, give it another node as a parameter, and then finally public void rebalance delete node as the parameter as well. Okay, so we're not filling these out here because in the standard balance tree class we just created, these are just skeletons here, so that when we create the AVL tree, splay tree, and red-black tree, we'll fill them out in those methods. And now to kind of test everything, I'm going to use the in order traversal. So public void in order node if node does not equal null, in order node.get left child, a custom print node class, in order node.get right child. Okay, the very last thing, and I promise we're done. I just copy and pasted these two print methods. This is just here to help us out with the testing so that we can see everything that's going on and we can go through it. Okay, we are officially done with coding the balanceable tree. All right, we are finally at the coding portion of red-black trees. So let's get started. I already created the red-black tree class, and we're going to say public class red-black tree extends balanceable tree. We created this already in lesson 10 when we did AVL trees, and we're going to use it for the splay trees and the red-black trees as well, because we're going to be overriding the rebalance insert and rebalance delete for red-black tree as well, and a few other things also. Okay, so let's go ahead and fix this error really quick and create the public red-black tree constructor using the super value. We need some auxiliary methods for coloring the nodes, checking if they're red or they're black, or making them red or black. So let's say private boolean is black, node as the argument, and we'll just return node.getHeight property equals 0. The getHeight property is used for AVL trees and red-black trees. Splay trees don't care about it. And the red-black tree, if it's 0, it's going to be black. If it's set to 1, it's red. Okay. And we'll do the same thing for isRed. Private boolean isRed, node, return node.getHeight property equals 1. Okay, so we're just checking to see if the node is black or if it's red based on the height property. Next one, private void make black node is the argument, node.setHeight property 0. Okay, so we're just going to take in a node and then set its height property to 0, so that's black. Then we have the one for red, private void make red node.setHeight property 1. So we just take in a node and set its height property to 1. Then we have one more, private void set color, take in 2 arguments, a node, then a boolean. Right, so we say node.setHeight property this boolean, so either true or false. If toRed is set to true, then it will be 1. If it's set to false, then we'll set it to 0. Now, let's go ahead and write our rebalance insert method. And we'll say public void rebalance insert, taking node as the argument. So node. If the node does not equal the root, so if node does not equal get root, we have two methods. The first one is we make that node red, because when we insert, always make the node initially red. Then resolve red for that node. So this will check. We haven't created this yet, but this is going to check to see if there's a double red issue or double red violation. Or if it is the root, we're going to insert it. That means it's black. If it's not the root, then we make it red, and then we resolve if there's a double red violation. We haven't made that method yet, but we are about to. So let's make it. Private void resolve red, take in a node as the parameter, and we're going to declare 4 different nodes. So node parent, sibling, middle, which I'll explain soon, and the grandparent. All right. Parent equals node.getParent, just to kind of make it easier instead of always saying node.getParent. If it's red, then we do have a violation. If it's not, then we just simply don't do anything with this method. All right. But if it's red, so we had the violation, that node sibling is going to be equal to sibling of the parent. We will create this method soon. So now that we have the sibling, which is needed to see what we do next, okay? So if the sibling is equal to null, or the sibling is black, so is black the sibling, middle, this node here, equals restructure of the node. So node, what we inserted, remember, that will be labeled X. So we're kind of giving this restructure method that we created in the balanceable tree, the node. This is going to do all of like the rotations for us, all right? And it will know whether to do a single or a double rotation. The middle node is when we do the restructuring, what becomes the root of this subtree, okay? Well, now that we know what the root of this subtree is, so it could be X or Y, we're going to make that node black. So make black middle, and then we make the children nodes red. Okay, so make red middle dot get left child, and then make red middle dot get right child. Okay, so we finished the case where if the sibling is black. All right, now we need the case where the sibling is red. So else, we just go ahead and make black the parent and make black the sibling. Grandparent equals parent.getParent. So we have X, Y, and Z. We have the inserted node, its parent, and then the inserted node's grandparent. If the grandparent is not the root, then make the grandparent red. Okay. If it was the root, we're done. It's going to stay black. However, if it's not the root, we make it red. And then we have to say resolve red grandparent, because remember, it could propagate up. Again, we don't know, but we need to check. Okay, so this is our check. We tell it to resolve red for this grandparent, or when I explained it, this would be Z. All right, well, we're done with that. Let's move on to delete. Public void rebalance delete, and node as the argument. If this node is red, so if is red node, then make it black. Okay, so if the node that we deleted or that we promoted, if it's red, just make it black. We're done. Okay, we talked about that when we explained it. Otherwise, meaning the node to be deleted is black and the promoted node is also black if it needs to be promoted. We say node sibling equals sibling node. So we just kind of create a reference to the sibling of this node, all right? Or of the node that was promoted. All right. If is internal this sibling, okay? Especially if this sibling node has at least one child. And if the sibling is black or the sibling dot get left child has at least one child, okay? Then we need to do the remedy double black problem. We haven't created it yet, but we are about to. So remedy double black the node, okay? We check if is internal the sibling dot get left child, because if it's not internal, that means it has two null nodes. All right. If it doesn't, then I mean it could be. Then that means it could have a red child. Okay, and that's also one of the cases. Now let's do the whole remedy double black method. This is a little involved. So private void remedy double black takes in a node as the argument. So node. When we do this, we didn't care about X, right? We only labeled the node and then Y being the sibling and then Z being the parent of the promoted node, okay? So node Z equals node.getParent and node Y equals sibling node. So if the sibling is black, so if is black Y, we say if is red node.getLeftChild or is red node.getRightChild. Okay, so remember the case was if we have the sibling node and one of its children are red. That's what this is checking for right here. So if one of the children is red, then we say node x equals is red y dot get left child question mark, meaning if this is true, then node x equals y dot get left child. Otherwise, node x equals y dot get right child. The otherwise is the colon there. Node middle equals restructure of x. Okay, so we're going to return the root of the new subtree after we do some restructuring. Okay, so it could be X or it could be Y, depending if we need to do a single or a double rotation. All right, then we set the color of this node if a Z is red. Okay, so remember, we take this middle node, or whether it's X or Y, the root of the subtree that we're working around, we take the former color of Z. Okay, so if Z is red, this is going to be true. So when we use the set color method, we're going to set middle to be red. Otherwise, it's going to be false. Make black middle dot get left child, and make black middle dot get right child. Otherwise, if none of the siblings' children are red, we say else. We make red Y, the sibling, we make it red. If is red Z, remember, Z is just the promoted node's parent. If it's red, then make it black. So if is red Z, make black Z. Else, if Z does not equal the root or get root, then remedy double black at Z. Because remember, case 1 is the only terminating case. Every other case isn't necessarily terminating, okay? So after all that, all of this so far has been if the sibling or Y is black. If it's red, the last case number 3, we just rotate around Y, we make black Y, then we make red Z, and then remedy double black, we call this method again on the node that we promoted or deleted, okay? Because again, case 3, you have to check case 1 or case 2 again. And then from there, eventually you'll get to a terminating case. And then finally, we have one more method, and this is the sibling method we've been kind of using. So let's go ahead and fix that. We'll say private node sibling node takes in one parameter. Node parent equals node.getParent. If parent equals null, then just return null. If node equals parent.getLeftChild, then return parent.getRightChild, else return parent.getLeftChild. We're taking the node, we're getting its parent, and then we're basically getting the other child of that parent, okay? And that's the sibling of the node we're giving it in the parameter or the argument, all right?